So let's calculate values of entropy. Much like enthalpy, we could actually use formation values or Hess's law to determine the entropy of a reaction itself. And the process is almost identical. The only thing that's different about it is that the units of entropy are not kilojoules per mole. The units of entropy are actually joules per mole Kelvin. But other than that, the process is still the same. You're going to have formation values for your reactants, you're going to have formation values for your products, and this time around, it doesn't actually matter if your element is in its elemental form, you're going to have a non-zero value for that specific substance. So all that changes really is, aside from the units, is that instead of having delta H of reaction, now you have delta S of reaction. And instead of having delta S products or delta H products or delta H reactants, you now have delta S product and delta S reactants. So the process is literally the same thing as what we did before. We take the values of delta S products, multiply by their balancing coefficients, we add them together. Take the delta S formation values for the reactants, multiply by the coefficients, and we add them together. And we input the values, we carry out the multiplications, we continue by adding the values for the products and the reactants, and at the end we subtract the value of the reactant from the product, and then we divide it by one of the reference points, which in this case I'm sticking to C2H2. So the entropy ends up being negative 216.14 joules per mole Kelvin, and this is the one thing I do want to highlight. The units for entropy are going to be in joules, unlike enthalpy, which has values of kilojoules per mole. So just be aware that you're dealing with a slightly different scale. So in other words, values of entropy tend to be about 1,000 times smaller than those of enthalpy. Not to say that they don't play a role and they don't affect things. They will and they can, but at least at face value, yes, enthalpy is a lot higher in its magnitude than the entropy is. Alright, so we're going to put that in there, and eventually I'm going to address the fact that this is negative and trying to convey to you what it actually means. What I can tell you right now is that negative values for entropy represent the states from which, going from reactants to products, you have decreased the amount of randomness. So instead of having a much more chaotic system, you have become a little bit more orderly in fashion. And that could mean that you have less molecules than you used to have, or it could actually mean that you change the states from maybe gases to liquids or liquids to solids, which tends to order your system more and more and more. Alright, but before we get into all that technicality, let's take a look at Hess's law. Now we've technically solved this problem already for delta H, but we're going to apply it once more to delta S. And you're going to see the procedure is literally the same thing. It's almost copy and paste. You have entropy of reactions for the 4 reactions down here, and you're interested in finding out the entropy of the reaction that I have highlighted up here. So you do the same thing. Recognize that the first equation has 1 mole of the product that you want, in the correct site with the correct amount. So that means that you lock the first equation in place. Then, looking at the second equation, you have C2H2 on the left side, 2 amounts of it. You only want 1 mole of it, so you multiply the entire thing by 1/2. And not only do you change the coefficients of the reactants and products, but you also change the amount of the entropy. You multiply by 1/2. Alright, then because we have the correct amount of C2H2, that means that the third equation is locked in place. Moving on to the fourth equation, paying attention to water and the fact that you want only 1 water on the left side, the third equation has water on the right side locked in place, so that means that you have to move the equation around, right? Products become reactants, reactants become products, and the negative 163.19 joules per mole Kelvin that you had for the entropy becomes now positive 116.19. Then you multiply that equation by 2, so that you end up with the proper amount of waters, which means that you also multiply the delta S by the proper amount, basically 2, to come up with the correct amount for the newly balanced equation. Okay, now the fourth equation is locked in place because if we change it in any way, we will affect the amount of waters, which will mess up the amount of water that we want to end up with. So the second equation needs to be changed now such that the amount of graphite is changed. And specifically, we want to end up with two graphites on the right side of the equation so that we cancel out the C graphite altogether. The reason being, we don't have it anywhere on the desired equation. So we move the equation, basically move the C graphite to the right side, CO2 to the left side, and the value of the entropy is changed to negative. Then you multiply by 2 to come up with the proper amount, meaning that you also multiply delta S by 2. And once this is done, everything is ready to work out. The two C graphites will cancel out, your two CO2s will cancel out, your oxygens, 1/2 plus 5/2, which is equal to 3 oxygens, is the same as the 2 oxygens and the 1 oxygen on the right side, which is also 3, so they cancel out. Your 3 H2s on the left side partly cancel out with the 2 H2s on the right side. Your 2 waters on the left side partly cancel out with the 1 water on the right side. So you end up with the desired equation. And much like enthalpy, you end up adding up the values of entropy, which we've been changing along the way. So now that you can add all the equations together to yield the desired equation, you can finally add up the values of delta S together to give you the value of the reaction, in this case negative 244.57. Alright, so now let's properly address the sign of entropy. What does it mean to have positive entropy? What does it mean to have negative entropy from the context of chemical reactions? The idea with entropy is that for you to be in a much more disordered state, in a much more random state, that means that you want to go from a physical state where the atoms or molecules are close together to one that is higher distances from each other. And the way you can make that happen is by moving over to higher temperatures, right? Because higher temperatures ultimately can lead to higher entropy altogether as a result of the fact that solids can turn into liquids, or liquids can turn into gases, or solids themselves can turn into gases. The idea, though, is that the molecules are being separated, they're farther apart from each other, so they have more freedom of movement. And that freedom of movement ultimately increases the energy, right? Because the one thing to keep in mind is that higher temperature equates to having higher amount of heat, and higher amount of heat ultimately yields to higher entropy, even though technically speaking you're changing the changing heat by the temperature, right? So there's a little bit of a dual effect taking place here. One does the opposite of the other one, but generally speaking, increase the temperature, increase the amount of heat, and that tends to be more of a change than just the increase in temperature alone. All right, so going from solid to liquid will increase the entropy because you have more modes of moving your energy around by the fact that your molecules are farther away from each other and they can actually use some of the energy to translate to farther distances. Same thing can be said for the gases. But if the changing entropy decreases, meaning that it's negative, then you're basically doing the opposite. You'll be going from a liquid to a solid, or from a gas to a liquid, or potentially from a gas to a solid. And what that ultimately means is that when it comes down to delta S's of formation, yes, you can definitely have different values for the different states of the molecule, but the one thing I want to highlight is that the entropy of the solid is in fact lower than the entropy of the liquid, which in fact is also lower than the entropy of the gas. And the gas by far is not only the higher value, but it's higher by a lot more than either the liquid or the solid. So let's take a look at what we just did with the Hess's Law example. In the first equation, we had, okay, see graphite, that's basically a solid. We had 1/2 amount of gas molecules plus another 3 gas molecules, so we have 3.5 gases plus 2 solids, right? And on the right side, we only have 1 liquid. Now, technically speaking, yes, you have turned solids into liquids, but you have turned more gases into liquids. So you would predict quite reasonably that the entropy probably has gone down because a lot more gases are turning into liquid than solids are turning into liquid. And since the gases tend to have a much higher, like a lot higher entropy values than either liquids or solids, converting gases into liquids is definitely not going to be undone by solids turning into liquids. So we would expect the entropy to be negative. And if you look carefully at the actual value, the value we calculated was negative 344.5, which is in fact negative. So just by looking at the type of molecules you have in your reactant and product portions of your equation, you can make the prediction for the sign of delta S. Now for the second equation, you have two gases on the left side, you have two gases on the right side, and two solids. And you might want to say, it's like, well, you have more stuff on the right side, you got still two gases, and you still, and now you have two solids, so technically you increase the entropy, but that would be a little bit not disingenuous per se, but it would be the wrong way to look at it, because yes, you do have two gases and you have two solids, but this came at the expense of the masses, right? Because the masses on the left side are going to equal the mass on the product side. So if you start with two gases, by mass, you had more gases before. Now that some of that amount has gone into making some solid, the mass of gases present is actually less than what you had. But granted, you still have two gases on both sides. So even though some of that amount has gone away to make some solid, we expect the entropy to change a little bit in the negative realm, but probably not by a lot. And if we reassess what we got before, the changing entropy was barely negative 10. So it's almost like in the neutral state, right? Because you have two gases to begin with, two gases to end up with. Here you just kind of have to like think about the masses. You know, you had more mass of gas before than you do now, which makes the slight difference. Now for the third equation, you have 1 mole of gas plus 2.5 moles of gas, so that's 3.5 gases. Over here you have 2 moles of gas, and you have your water molecule, which is a liquid, right? So you only have 2 moles of gas and 1 liquid. And needless to say, more gas is always better. So it looks like the third equation is also of negative entropy, and in fact the value was negative, as you can see. Okay, so finally, we look at the last equation. We have 2 moles of liquid, which turn into actually 3 moles of gas. So we go from 2 liquids, now gases, 2 liquids to 3 gases. So that's a definite increase in entropy, not only in amount, but also because we went from liquid to gas. So this is, unsurprisingly, positive 326.38 joules per mole Kelvin for the entropy. And finally, looking at the final equation, we have 1 mole of gas, 2 moles of gas altogether, and 1 mole of liquid for the reactant side. And on the product side, we only have 1 mole of liquid. So clearly, everything has turned into liquid. You have decreased the entropy, so the final entropy here should be negative. And the value we got was, in fact, negative. There's a kind of neat way of approaching what's happening to the entropy in terms of what kind of substances you have. Do you have liquids? Do you have gases? You know, what's the story? You will not be able to get the actual value itself, but you'll be able to tell whether it's negative or positive. And I might ask you to do that for some of the determinations that we're going to address in the next lecture series. So with all this being said, this is the end of the lecture. So I'll finish the video right here, and I will see you on the next one. So talk to you then.